Okay, so let's start to look into that. So today we're going to discuss the chapter 3 for the industrial motor. So chapter 3 mainly looking into the torque equation and also equivalent circuitry. So have a quick survey. Sito, have you working on the equivalent circuitry for motor before, for industrial motor before? Have you done industrial motor? Like
No.
equivalent circuitry, no? Haven't.
Equivalent circuitry.
Like the circuit model for industrial motor.
No, yeah.
Okay, so today we're going to looking into the torque equation for industrial motor. We're also looking into the power formulation for the industrial motor. So this equation highly related to slip and the speed and also the torque equation. Firstly, I'm going to show you a few tutorials so that to support you how to work out the homework. So the target question we like to look into will be, what is the best way to understand more about the starting torque? What do you think the industrial motor starting torque? We've been working for the DC motor starting torque. We know the DC motor have a really strong starting torque. But how is it compared to industrial motor? What do you think? Which one would be better? Manfia, what do you think? Which one have higher amount of the starting torque?
The DC one.
Yeah, DC motor. The thing is, DC motor may start the back EMF equals 0. All the current will be coming out from the RA, from the resistor. So a huge starting current. But industrial motor doesn't like that. The starting current depends on many things. So that's why starting current, although all the current usually proportional to the torque, but its starting current is large, but not as large as the DC motor. So the DC motor have much higher torque than industrial motor. And later on, I can show you some characteristics, then you can see how they look like. And then we also know that the slip, we've been talking about the slip for quite some time. That will be really much near, close to the motor torque. So we do have a correlation. We can look into that. And then we also see that for very speed of the industrial motor, maybe for slip, we do have something related to the torque. So the slip is the difference between the synchronous frequency to the rotor frequency. So the difference between these two will be the slip. So that means we can transfer anything about the rotor speed into the slip anyway. So if you look into the torque speed characteristic, you can see that the horizontal axis will be the speed. Sometimes people will also annotate them into the slip too. So either method, we can use it to look into that. So for the slip, you can see then we can also use the slip to understand more about which region the motor under power regeneration. I think we're also looking into DC motor power regeneration. And even though for industrial motor, we do have the region for power regeneration, we're going to look into that. So usually power regeneration, we tend to make the input voltage slightly less than the voltage generated by the motor. So in this case, for this motor, we got a back EMF. How about for industrial motor? How does it look like? We're going to examine what it is. Another thing will be the rotor resistance. And last we learned about the rotor resistance mainly come from the rotor bar, right? So we do have some resistance, although the resistance is quite small, quite low. But we do find that the rotor resistance highly relate to the output power for the industrial motor. So we're going to examine about the characteristic. So today we're going to look into a few areas, including we're going to revisit about the slip and the speed, how that look like, and then we're going to have some tutorial to look into that. We're also looking into the operation, various operation mode we have for the industrial motor. We also go back to revisit the three-phase system. I think you all know about three-phase. Then we just spend a little bit of time to understand more about three-phase, and then we try to look into the torque and speed modeling. And then the efficiency, we're going for some tutorial. So that's how we configure this week. So first of all, share the application. I don't know what that means. move away this window, away from the shared application. So the power flow in this motor very important. We know the power from the stator. When you go in the stator winding, then you move on to pass through the stator resistance, like the copper, and then you go to the air gap. Then you produce the air gap field. The air gap field will travel from the stator to rotor and reach the rotor. Then you generate the induction. Then you become the current flow. So roughly about this. And then that induction will create us with the motion. Once we got induction there, then we create current in the rotor. The rotor current together with the air gap flux will therefore produce the rotational force. So that briefly about what happened. So in this case, it's better we can model the whole system by using some circuit modeling, which we usually using the circuit model to understand what it is. So one of the issues would be so-called the air gap power. So air gap power is the power flow through from the stator to rotor. So we're going to look into the air gap power, how that relate to the power from in the stator and the rotor, and also power output. We're going to understand more about each the power stage to see how the circuit parameters, which can able to use it to examine about the whole motor performance. From there, you can able to look into the efficiency and the power losses. So one item is the air gap power. What that means is the total power transfer from the stator to rotor through the air gap. So that is to say, you can see that if we do have a stator in here, then we have the stator to build up some rotating magnetic flux. So the magnetic flux will therefore building in here. And then pass through them, there's an air gap between them. And on the other side, we got the rotor. And motor can therefore, so we got the flux will go through the air gap to the rotor side. And then the rotor, once we got the field in the rotor, then we get the rotor conductor will conduct the current here. Then we therefore build up the rotor current. And rotor current can also develop the rotor field too. So that's why I can see that sequentially we can have stator current and then gradually move on to the rotor power. So that means you can see that the air gap will have the air gap power flow from the stator to rotor. And then if you want to see how the power being distributed, then we can understand more about this from this diagram, from the chart. So firstly, the input power will go through the stator, and then the power will firstly distributed in the rotor, become copper losses, of course. Once we pass through the stator winding, you can see that the stator winding formed by the copper. So that's the first domain to have the power losses. And then that will become the rotating flux, will therefore produce us with the air gap power through the air gap. So this power will go through the air gap to the inductor, so to the rotor side. And then rotor side will therefore produce the losses in the rotor. So there's also copper loss, I squared R losses. And the remaining will become the mechanical power. You see this mechanical power not only become the rotating mechanical power, but also have power losses due to friction or windage losses. So after this, then all the power will go to shunt. So that's how we see the power conversion look like. So that's a straightforward diagram. Then we can see what is happening for overall motor system. So before we go any further, we'd like to show you about how we have been working on the slip and the speed, because if you're not quite familiar with that, I will now show you a few tutorials so that you understand more about what it is. If you have done it in the past, that will be a revisit. Firstly, you can see that if you got 4-pole machine 50 Hz induction motor, under the low load system, the speed will be 1492. So you can see that the synchronous speed will be equal to 120 F1 over P. Anybody can tell me how that equation come from? How to derive the equation? Why 120? Where does 120 come from?
If 120 is from three-phase, right?
From where?
In three-phase, all
We're not talking about three phase yet. Yeah. Although most of motor, 70% of motor are three phases. But where the 120 come from? So that's F1 is the input frequency, 50 hertz, right? 50 hertz. We have 50 hertz go into the motor, and then we calculate the synchronous speed. So where the 120 come from?
That's to change it to the RPM.
Yeah. So we got F1 frequency, and then we multiply 60, become RPM, because hertz is per second. We need to RPM per minute with times second, and then divided by the pole pair, P over 2, right? As I mentioned, 2 pole mean 1 cycle, 4 pole half cycle, and then half cycle, right? So we divide by the pole pair. So that is how 120 come from. So you need to know that. And then the second question asks us about the no load slip. That means when without any load, you see the motor running much faster, more close to the synchronous. Because without loading, of course, the speed will be faster. That's a really common sense. So 1500 minus 1490 divided by the base value, we got the slip. So the slip ratio you usually will be in percentage or decimal. Yes?
Why did we do the P by 2, the pole by 2? Can you just explain that?
Could you say again the P?
The pole by 2. Why did we do that? Like 120 F1 by P, right? In the main formula, the
Yeah.
pole by 2, P by 2.
You mean this one?
Yeah.
So this move here.
No, I mean, why did we do this? Like P by 2?
Oh, pole pair, right? You don't get the pole pair. So for instance, one here, we got 4 pole. Here, 4 pole. Then every time the rotating magnetic flux will only travel from this to there. Half, only between the 2 poles. And the next will go into complete another one. So that's the mechanical speed and the electrical speed are different. The pole pair are arranged in such a way that when excite them with electrical signal, power signal, they only pass through 2 poles. Next cycle, another 2 pole and 2 poles. So that's why we need to divide by P over 2, the pole pair. So that's why I can see that 50 hertz, if you inflate this one, equivalent to 3000 RPM, right? But now we got 4 pole, so each time that 50 hertz, one period only travel by half a cycle, next another half cycle. So that's why mechanical speed will be reduced by 2. For most of the motor, then we have 2 poles, 4 poles, 6 poles, and so on. More number of poles, we got less speed. So that's how we come from. So the standard speed, so the synchronous speed or the base speed will be 1500 RPM. But you can see that when we without any load, the speed will be really much close to 150 anyway. So that becomes 0.53%. That's how we see that. And then the full load speed, of course, under the full load, the speed will be due to loading effect, we got less speed. So that's a common sense, right? More loading, the speed will be like slightly lower. Then we got 1440, and then the slip will become 4%. So you can see that from light load to heavy load become 0.something% to 4%. Then for any motor, if we naturally we don't have any speed control, you can see that when we have light load to full load, the speed will be changed. So and then the changes here, we call it the speed regulation. The speed regulation here will be just the high one divided by the low one and divided by the full load rotation speed, then we got 3.6%. That's the load regulation, how much the load being changed in various conditions. So that means this kind of motor, if we don't have any power electronic speed control, then when we naturally power up, when we change the load, the speed have changed up to 3.6% between the high speed and low speed. That's what we can see. So this tutorial just show you how we use this formula or this formula, and then how we understand use the sleep. Very straightforward. Just a quick tutorial to show you some basic operation, how we use the terminology, like the synchronous speed and also the load speed. Second question asks you how the frequency will vary. The example here will tell you about if you got 8-pole induction motor running at 3% on 50 Hertz. If now the frequency increase to 60 Hertz and the sleep unchanged. So usually for induction motor, certain amount of the sleep will give us the best performance. We usually try to control the motor to a certain sleep ratio. So in here, say 3% is they try to control it. Probably that's the best operation mode. Now we're going to calculate the original synchronous speed next to calculate motor speed. So again, we can use the same formulation. Then using 50 divided by the number of poles here, then become 750. So you can see that when we use 8 poles, we can divide by 4 for the input frequencies, then become 750. So you can see that when we use a more number of poles, the speed of the rotation will become much slower. That is reasonable because for many motors, we don't need a few thousand RPM anyway. For many industrial applications, like electric vehicle or industrial drive, or maybe even though the ventilation AC system, a few hundred will be more reasonable. A few hundred RPM will be at least 10 rotations per minute, more than 10 rotations per minute. That is good, more than enough, right? Then from there, we can also work out the speed, the original motor speed. So that means we have 3% here. So that 3% means the difference between the synchronous and the motor speed. So we drop by 3%. So 700 multiplied by 1 minus 0.03, then we got 727 RPM. So that means at 3% sleep, the motor speed will tend to become 727. Motor speed will seldom or never go to the synchronous because at synchronous, there won't be any induction. When the rotating field is rotating, the rotor also rotating. So if they're exactly the same speed called the synchronous, there won't be any induction because there's no change. All the magnetic field induction need to have change in the induction because we know that the induced EMF equal N d phi dt, right? So if we don't have any changes here, there won't be any voltage induction in the winding, in the rotor winding. So that means we need to have different. So that's why these two must be different in order induction in the rotor winding. That's the principle for induction motor. So now then we've done A and B. So if looking into the new condition, now we have 60 Hertz here. So we're just using 60 Hertz in the equation. So the speed now becomes 900 RPM. So you can see that when we change from 50 to 60, we got slightly high speed. And then we do the same thing for the new motor's rotation, and mean rotation. Then we now have 873 RPM. So obviously you can see that the reduction from 900 to 773. Yeah. So the speed is now increased by almost 20%. So this 20% from this ratio here is the same as the from 50 to 60, also 20%, they're linear proportional to each other, right? So that means so this question is tell us if you want to change the motor speed, we need to change the input frequency. So that's also one of the criteria for the inverter. The inverter, actually, we are changing the motor, apply the AC frequency to do that. So without changing the input frequency, we have difficulty to change the motor speed anyway. So that's some typical method we do that. And another terminology to show you is called the breakdown sleep. So you see a motor will break down in certain condition. The breakdown doesn't mean the motor disintegrated. That means this is a terminology at which the maximum possible torque will appear. So when we are able to obtain the maximum torque, You see, when we change the motor speed, like engine or ICE engine, changing speed, the torque will also be changed. So for motor as well, when we have constant work done applied to the motor, then when we change the speed, then the motor torque will vary. So this variation will change with the time. So probably you can see that if the speed here, the motor torque in here, then we change to something like that. Usually all the curve like that, we have maximum somewhere in the middle of the operation. OM will be lower torque. And then this maximum here, we call it the maximum possible torque here. And this also called the breakdown torque level. And then the slip, we call it the breakdown slip SM. Yeah. So that's how we define the terminology here. So at the breakdown, then we can see that when motor reach the breakdown slip, we can deliver maximum possible torque for the system. And then we also see some phenomena later on. I will explain in more detail about that. So at the breakdown point, that divide the motor in two regions, left and right hand side. They see that one of the region, the motor become more stable. Like here, this becomes stable. And this one region become unstable. Later on, I will explain to you why it does that. And so that means when we operate motor, we tend to quickly to move the motor to stable region for the operation. And then in the unstable region, we call it the point of no return. That means once operate in this region, any fault in the torque control, then the motor will going to stall, can stop. You cannot move it back to the normal. So that's why, especially for underload or overload operation, we tend to have that. So that means when any motor designer or control designer is working on this kind of motor, we need to ensure the motor will well below the breakdown slip. Yeah. So when the slip is lower than the breakdown, that is much better. You see, slip is the difference between the synchronous and the motor speed. So that means when you're below the breakdown slip, you try to make the motor more close to the synchronous, not the other side. So when we talk about the torque speed characteristic, then you can see much better. Then for the full load slip, so how much is the full load slip? You see that's the maximum torque. We never operate at maximum torque. Just like a power supply, you can operate at 1 kilowatt. We never always operate at 1 kW power. We just make it slightly less than that so the system become more comfortable. For instance, a human being, you can live about, say, maybe 200 kg. You will never operate 200 kg all the time. You will operate something less than that. How much less? 25 to 50 will be more comfortable. Like human being, like maybe like what you can run. If you can run maybe 100 meters in 10 seconds. Every time when you go out, you won't run at that kind of speed. You only walk and run is slightly less, maybe 25 to 50. So that's what we're looking into. Our full load operation, you never use the breakdown value to do that. That's because that's the maximum. We're always working on roughly lower, say 25 to 50% lower compared to the breakdown. So that's what we try to operate, right? So that you define what's the meaning of breakdown, what's the full load speed, full power operation, and the maximum capability called breakdown. So breakdown means more look like that's the maximum value. Beyond that, will break down the system. So, yes?
I have a big confused. So the full load slip, say 25 to 50% of breakdown slip. But if the slip is increased above the breakdown slip, the torque also will be increased. So I confused. Is 25 to 50 difference or 25 to 50 less to the breakdown slip?
The 25 to 50, this percentage depends on the motor. All motors are different. Roughly about 25 to 50, that's the normal range of operation. Like for instance, the breakdown force you can lift up, say, to maybe 200 kg. but you won't always operate at 200 kg when you lift up something. You usually operate at around 25 to 50% of the 200 kg when you normal doing exercising, right? That's what you mean. And then for the motor as well, we got two regions here. Later on, you can see more clearly about these two regions. We have two regions here. This region is the maximum possible of the torque you can generate. And then we mean the 25 to 50% will be this region.
Okay.
In this region, we don't operate them. It's too dangerous.
Okay.
The motor will stall. We not try to not even think about that.
Okay.
So this is the phase safety margin we try to fulfill for motor operation. In this page, I only show you the terminology for breakdown. We haven't shown you the curve. Later on, after a few slides, I will show you about the curve, how the breakdown curve shall look like. At the moment, you just understand what's the meaning for breakdown, which means the maximum possible torque. I think you can imagine breakdown is maximum possible. Beyond this one, more than this one, the motor will really break down, you damage the motor. So that's kind you can call the breakdown slip or the breakdown torque. Or sometimes we're going to pull out. After this, the system will pull out. Yes.
For any motor, we can control, right? Like we can properly control a motor at like what range we need it to work at, right? So 25%, isn't that like way too less?
25 to 50,
Yeah,
the range. Just for instance, for motor normal operation, So just like for you, you can lift up 200 kg. Then for your normal, 200 kg is your maximum you can lift up. More than 1 kg, you crash down. So the maximum possible operation you have. But for normal daily routine, will you always lift 200 kg? 24 hours? You won't. You damage your body. So that means we normally only operate at about much lower, 25 to 50 for normal operation. That is the breakdown value, the maximum possible value you can sustain. Not you can sustain, you can maximum afford to do that for that particular motor. You can still do that, depending on the motor design. If some motor design, they can always work on the maximum, they can do that. But the thing is, once you operate on here, once you reduce the torque, you have dangerous to reduce on that side or that side. Once you go that side, the motor really easy to get damaged, not damaged, stalled. So you try to work on this region. So this region, how you can slightly further away from the maximum possible value, you are more comfortable to work on this region. So 25 to 50% of the maximum will be something more comfortable, more sensible. Of course, if your controller is good, really good, you can always operate on this region very close, maybe 10% away from the maximum. That also be okay if you're able to do that. But you need to have really good speed control. Make sure the speed will not go further down. Otherwise, become load called the point of no return. Or if your motor has really good cooling system, you can remove the heat quite really well. Then you can afford to really close to here. So what I'm saying 25 to 50 doesn't mean the absolute value. It can be anything. It can be from 10% to 90%. The normal motor says 20, 50 will be quite reasonable. If you get really good cooling, you can work up to 90%. If your speed control is excellent, probably 99, probably you make use fully use tonight. Like Tesla motor. Tesla, they won't work at 25 because they got excellent cooling. They will maximize their motor power to about 90% because they use liquid force, high-speed liquid cooling. But for normal industrial dry, like the water pump in your home, you won't operate at that because it gets really hot.
Yeah.
So that's what I think, yeah. Anyway, so in here we say, another thing we can see that for slip and torque relationship, let's see. Just so if we have a 6-pole machine, 60 Hertz, and then the motor delivered a maximum torque at 900 RPM. So we calculate synchronous speed, and we also calculate slip at the maximum torque and motor speed at the full load. If the full load slip only 40% compared to the breakdown value. So let's redo that. So 60 Hertz again, then we need to use 60 here, divided by the 6 number of pole become 1,200. Very simple. Use the formulation. And then the slip at the maximum torque. So that means we just putting 900 into here and the synchronous into here. That's all. Then we can get 25%. That's also simple and straightforward. And then we say the full load slip. The question is say the full load slip only 40% of the breakdown. So that means 20. So this 25% here, and then 40% we put into here, then we got 10%. That means the full load slip is now 10%. So now then we can put the full load speed now. We got the reduction for 10% multiplied by synchronous, then the full load speed will be 1,080. That's all. So this is a typical calculation we did when we were in undergraduate. I think in undergraduate, if you learn about industrial motor, probably most of you may have learned them in the past, but maybe after so many years you have forgotten. So that's a typical straightforward calculation related to the slip and the speed, right? Next question, you say if a conveyor system try to require motor to operate and approximate 700 RPM, you now design a conveyor system for 700 RPM. So you now provided with 60 Hertz because our system is 60 Hertz. What kind of motor you're going to select? So we are assuming 4% slip is the proper operation for full load condition, right? So let's do that. So we just select thinking about using 10 pole, 8 pole, 12 pole, different pole number to see which one would be more suitable, more close to 700 RPM. So firstly, we use 60 Hertz in here, and then we use number of pole, 10 pole in here. Then that calculation gives us 720 RPM. So that is the synchronous speed, not the motor speed. So if we say the motor will be 4%, we put in 4% in here, then we get the motor speed for 10 pole will be 691. So that will be really much close to our ideal condition, 700 RPM. And then we can try 8 poles motor. We do the same thing again. So 60 Hertz into here, then we use 8 pole of motor. Then the motor speed will be higher, become 900 RPM. After reduction for the slip, then we have 864. So this is far too high, higher than the conveyor. Because conveyor require this one. So this is slightly faster. And then next, we try to use a slower motor, 12 pole, right? So that means we're now using 12 pole here, become 600 RPM. That would be far too slow, not matching 700 RPM. After deduction for 4%, become 576. That would be too slow. So for 3 of the motor, it seems the 10 pole will be more reasonable because more close to 700 RPM. So that means we choose this one. So that is to say, in some time before we have power electronics, when we want to control motor speed or we want the low-cost solution, sometimes conveyor, you don't need any speed control. Even though you have loading effect, you change 2%. So probably from conveyor, say conveyor in the airport, you don't need to care too much about the speed. You don't want to use inverter. You want to save money. So you just try to use 60 Hertz. You want 700 RPM. You just select any one of the motor. Which one is the best? Then in this case, you see that 10 pole will be the best. So that is to show you how we select a motor. Because in the market, you can buy 2 pole, 4 pole, 6 pole, 8 pole, whatever pole. So anyone. So that is something we can for our design. Of course, in the future, when you have the investment for the inverter, you can use speed control. But inverter also quite expensive, more expensive than a motor anyway. So next question, we're looking into something related to the air gap flux, air gap power. Let's look into that. For efficiency calculation, we're mainly looking into how the air gap power relate to the slip. There's a strong correlation between them. I'm going to go through the formulation, how we derive the formula. So probably you have seen that in the past, but in here I show you the calculation first. Because in the tutorial, we may need to do that in homework. So now we got 4-pole machine, 50 Hertz. So this induction motor try to draw 25 kW from the input. That's from the input, not for the output. You see, when you look into any motor nameplate, how much kilowatt? So that's a two kind of the thinking. The kilowatt usually refer to the output power. The output power is the real power. Sharp power is the real work done. So that means if a motor say 25 kilowatt, usually refer to output power. And then input power may be slightly more than that because you got the power losses. So bear in mind will be that. But in this question, you say you draw 25 kilowatt of the input, and then you deliver about 1450 RPM of the output sharp. So we know that the motor copper loss is 800 watt of power. So it's quite, you compare these two, it's quite a good portion anyway. So we are going to calculate the synchronous speed, the slip, the air gap power, the mechanical power, and the efficiency. Let's do that. So the first question, straightforward. We have 50 in here. And then divide by number of pole, we got 150 RPM. Now you're really much familiar with the motor now. 50 Hertz, 4-pole, 150 RPM, right? And then for the slip, then because the standard delivery is 1450, so we have this one, then we know that the slip at that particular operation will be 3.33%. Now the copper loss. So the copper loss in the rotor are actually related to the air gap by the slip here. That is a really important equation for the rotor circuitry. I haven't shown you that. Probably you learned in the past, but later on, after a few slides, I will show you where this formulation comes from. But just using this formulation first, then the copper loss of 800 watt in here, divided by the slip, will give you the air gap power. So that is to say, you can see that in here, what we showed you just now. Air gap power divided in two portions. S portion go to here. 1 minus S go here. Quite strange. These are some strong correlation. Later on, I will show you there's some relationship. Yeah. So before that, you may not believe, oh, why copper loss has some relationship? Yes, it does have that relationship. So later on, we'll see how that comes from. So now we can get air gap power. So you see the rest of them is the mechanical power. So air gap power, the ratio of 1 minus S will go to mechanical output. That will be 24. And then we give this output power. Then mechanical power. So now then the efficiency of motor will be output divided by the input. So output will be this one. Input will be from here, right? So the actual performance of motor will be 92.8%. So how we can get the efficiency. Okay. Have you done this calculation in the past? In your undergraduate a few years ago? I think you've done that. All the students have done that. I remember I did that, but that will be many years ago, 30, 40 years ago, right? Anyway, so that's a really simple calculation. I just revisit to you. I think you all have done that, but just refresh your mind, make sure you do that, because after that, we'll go to the torque and speed characteristic. From there, you can make use of this information to refresh your mind anyway. So next, we're going to look into the starting torque condition, right? The starting condition in here, we try to see the standstill means starting. When we say standstill, starting current frequency mean when the motor just starting, that means it's standstill. Standstill means not rotating, not moving. At that time, what kind of the frequency on current look like? We're going to look into that. Now we got 6-pole machine, 60 Hertz, have a rated speed of 1140 RPM. And then we firstly calculate synchronous speed, straightforward, just using the same formulation. We have 60 here, divided by 6-pole, we got 1200 RPM. Really standard equation. And then next we calculate full load slip. Because rated speed means the full load anyway. Full load means the weight, right? So that means we do 1 minus 140, then we got 5%. So you can see the 5% are roughly a typical parameter for full load sleep. Yeah, for full load. Low sleep usually less than 1%. Full load with 5%, 4%, 6%, depending on your motor. So more reasonable. And next, standstill, that means the motor is not rotating yet. It's going to rotate, going to start. So that means during that time, what is the starting current at standstill? That what kind of frequency would that be? So the current in the rotor during that time, we should check about the rotor. The stator we don't need to calculate, right? The stator must be 60 Hertz, always 60 Hertz because input 60 Hertz. How about the rotor? What's the rotor frequency? Why the rotor frequency I say will be 60 Hertz here? I don't need to reduce by the sleep.
Yeah, it stands still.
When the motor is standstill, that means the stator and rotor look like a transformer. No, just a normal electrical transformer, right? So the rotor is secondary side must equal to the input frequency from the other side 60 Hertz. So that means we'll have 60 Hertz here. Right? So we have formula, that's a S, right? Sleep. The synchronous is the input frequency multiplied by the sleep will be equal to rotor frequency. FR is the rotor frequency. Yeah. So S, the sleep means the sleep ratio between the rotor and the stator. Of course, stator equal to, say, N synchronous minus N for the rotor over NS, right? That's usually about the sleep. Of course, this equal to standstill 0, that must equal to 1.
This, it stands still, this rotor frequency is dead one induction.
Yeah. Part C is the rotor frequency. We're talking starting current frequency at standstill. We can calculate two frequency. The stator frequency always 60 Hertz. We don't need to calculate because the input. Another frequency could be appear in the rotor winding. That also 60 Hertz because it just look like a stationary transformer, 60 Hertz. And then from the formulation, we know that the formulation is rotor frequency equal to S multiplied by F1 input frequency anyway, right? That's the formulation. I'm not quite sure. I showed you maybe in previous page I showed you. So that's also equal to 60 anyway. So from two things, from formula we know is this. From the basic concept for transformer, we also know that it must be 60. Next question is say, when the rotor frequency is 12 Hertz, then we know that is the frequency, right? So 12 Hertz equal to the S multiplied by 60, then the sleep will be 0.2 from the formulation. Then that's why if we reduce by 20%, then we know that the motor speed will be 960 RPM. We also using the same formula. It's a very important formula we have been using. Basically, that means what kind of the rotor frequency it should be. If you have a current probe, try to measure the rotor frequency, we can see 12 Hertz there, much lower frequency than 60. That's what we meant here. As we also discussed last week about, I always ask you, what's the rotor frequency? You see 60 Hertz, 59 Hertz, 55 Hertz? Then our answer will be much lower frequency, just a few Hertz. Yeah, that is the rotor frequency, which is really low. It's the difference between the theta frequency and also rotor speed. Higher the rotor speed, the frequency will be lower. Yeah. If the two speeds are equal, we have no frequency in the rotor, no induction. That's what we meant here. All right? Okay, that's an important concept. I think I told you before, I had been teaching motor for the last 40 years. It's many students, even though they've done motor for a long time, they still don't know the rotor frequency is small frequency, low frequency. They always told me 50 Hertz, 49 Hertz. That's not true. Because for induction principle, you cannot have low 50 Hertz there, 49 Hertz, you're low in induction. You need to have relative motion between them. Anyway, so next we'll be trying to look into the multiple speed operation. So we have 4-pole machine here and 50 hertz here. And then we try to operate a 3 kind of the load. So you can see that at light load, the speed usually will be higher. At heavy load, the speed will be lower. That's reasonable. That's called the loading effect. It appears for motor, whatever. Just like a battery, if you connect more load to the battery, the voltage will drop more. Even though for this power point, 120 volt there, if you connect more load there, probably you can see that the voltage on that power point, when you measure, will be less than 120, maybe 119, 118. When you take out the load, then the voltage will go back to 120, maybe even higher. Usually for the power distribution from PG&E, they tend to make the voltage slightly higher. That means in case you connect heavy load, the voltage won't drop by too much. So that means loading effect. Loading effect appear for all the power supply motor too. So when we have heavy loading, the speed will be changed as such. So now then we need to calculate the slip speed and rotor frequency for each of the scenario. Firstly, we calculate synchronous speed. So standard formulation, we got 50 here. Then we can therefore calculate number of pole, 4 pole. Then we can get the synchronous speed 1500. We've done it many times now. So we're really much familiar. 50 hertz, 3000, 1500, and so on, right? So now then we got synchronous. Then let's do that calculation. So for light load, we have 1470, right? So 1470 here, then we can, this ratio, we therefore get the slip 2%. And 2%, similar 1440, we can get 4%, and 1410, we got 0.06. Obviously, you can see that when you change from light to heavy load, then the slip will also change. The slip is not the speed, it's the difference from the top synchronous speed. So more loading, the motor gets slower, the slip will become larger, more different. That's what we meant, okay? And then for the slip speed, right? This is the ratio. Now we change the slip, is just simply this, right? 1400, the 150 in here, that's the difference between two. So you can see that the slip speed means RPM, not frequency. Frequency will be hertz, but speed means RPM. Then you can see that it increased from 30 to 90. That's really much reasonable too. So now then next, you calculate rotor frequency. How much is the frequency of current inside the rotor circuit? So that is, again, we use the slip here, calculate with the frequency of input from the stator. So remember, the 50, we don't need to divide by 2 here, no need, because frequency. Electrical frequency, you can't change the electrical frequency by number of pole. You can see that that's like a transformer. You can't use transformer to change the frequency. No matter you put how many pole in the transformer, it's still the transformer, electrical induction. Okay, but rotation you can change. So that's why I can see that we have the frequency also change in such a way. So you can see that in here, light load, we got low frequency in the rotor. When you heavy load, we got higher, slightly higher frequency in the rotor circuitry. But still, they all is a low frequency, just a small frequency anyway.
Why is like that? If you're using heavy load, then frequency is increasing?
Yeah, that is the rotor frequency, the current flowing in the rotor bar, rotor winding. The key reason you can see that here. When you have a heavy load, of course, the rotor speed will decrease. It must decrease. You can't more loading the motor running faster, impossible. Low motor. That's loading effect. So once you do that, then the frequency will be like that. More different. The difference will go to the rotor frequency. Okay? That's the concept you need to understand. Not many people get that. Initially, you may think, oh, impossible. Why the frequency will be like that? Mainly, induction motor principle is the difference between two frequencies with induction. You can imagine that when you have heavy load, the motor itself want to have more induction to generate more power to compensate. That's the physical phenomenon. So that's a kind of internal feedback. When you pull more low torque, the motor have a more different in frequency, more different, they will generate more electromagnetic induction, try to generate more torque. That's what you try to do. Okay. Later on, you can observe this phenomenon from the torque speed characteristic. So that's a very important point about the.
So here, if you are using heavy load, speed is decreasing.
Yeah.
So I mean, so difference between static and rotor speed, due to increase in the difference, we have high inductance, right?
Higher induction, not induction, induction.
Yes.
Higher electromagnetic induction, then we get higher torque generated. In order to compensate for the high heavy load, that's the lateral phenomenon, internal feedback for the induction motor. That's really important concept. Yeah, so that's why I recall you. I think you have done that 10 years ago, but now I recall you. So make sure you understand this concept, how we understand the internal feedback for induction motor. Okay. So that's why the way I teach will be different. Other professors just showed you the equation. They didn't explain to you what happened to the induction motor internal feedback. They internally, they can readjust the slip, speed, and the torque, provide this kind of capability. That's how we make sure the motor should operate in this particular region. That is the region we like the motor to be. Later on, I'll show the speed torque characteristic. You can fully understand what happened. All right, get that? So every time when we visit a topic, we can learn something new. Maybe only you learned it 10 years ago, but now when you revisit, you can think a bit more. You can now understand why we need to do that. Oh, because we have an internal feedback in the induction motor. You're able to do that, can compensate for the extra torque requirement. So that's how it happens in the induction motor. All right. So the operation is different from DC motor. We don't have that kind of special operation. So induction motor is really funny. So it's nice to discuss that. So the key point we have here will be our slip speed is a mechanical speed RPM, not really a percentage. We have the slip ratio, slip percentage. When we talk about slip speed, then we have to use the RPM, right? RPM to do that. So it represents how the motor lagging behind the rotating field. Rotating field is the electro from the stator, right? So when the motor is lagging behind, then it produce more lagging, more different, then can produce more induction. So the load will increase. As the load increase, the motor will slow down. That's reasonable. And the slip speed will also increase. Then you can generate more relative motion between them. That's why we got more induction. Then the induction higher, and then the torque will therefore become higher. That's what you mean try to do here. So the relationship will be, firstly, the slip, we use it using the percentage, like a decimal or something in percentage. And then we can also have the slip speed. Slip will be RPM, right? Will be S multiplied by the synchronous. So that's what we're trying to differentiate. Because sometimes people may be a bit confused about the slip speed and the slip. These are the two terms. One is a ratio, one will be actual RPM. So, I just try to show you some typical parameter for motor. You can imagine how motor slip look like for typical motor. So for heavy load, then the slip may increase to 6%, quite a large number. So usually light load will be 1%, 0. Something, 0.9, but heavy load can go up to 6%. So 6% for a two-pole machine can equal to 90 RPM. For light load, usually really like can be just within 1%, maybe maximum 2%. Of course, that depends on what kind of motor we tend to use for large or small motor. For small motor, say less than 10 horsepower, then the light load slip will be like that. And then for large motor, a few hundred kilowatt, then the light load slip can even smaller. So that's a typical range. You can see that, but once we go to heavy load, then probably it may go to 6%, maybe 5%, and 7%. It's quite a big value anyway. But so that's how we typical parameter. So the sleep will be usually just a few percent. You seldom go to 20%, 30%. We don't do that. Later on, you can see why it happened. So now we go to a beautiful curve. That's the important curve for the torque speed characteristic. I think everybody have seen that curve in the past, like so-called torque speed characteristic. So that's the speed characteristic. So obviously you can see that here will be motor starting. When motor starting from the zero speed, then we got certain amount of the torque, not equal to maximum, but the torque will be reasonably large as compared to ICE. So when the speed are increasing, then the curve will go to a maximum torque. That's a really maximum possible torque. Just like what I mentioned is the breakdown torque. So this region, we call it breakdown. Breakdown torque, breakdown slip, they all in that region. And beyond this region, then the torque will start to reduce. And then at that point, because slip is equal to zero, that means the synchronous speed equal to rotor speed. The two rotation field and the rotor you same speed, that means no induction. So at this point, no induction. So that means the torque, no induction, of course, we have no output generated. And then beyond this one, then we got the power regeneration, go to the quadrant 2, right? But we don't talk about it yet. So let's look at this region. That's really important region. So although the horizontal axis equal to the speed, of course, we can also write down the slip. Slip means the difference between the synchronous speed and the rotational speed. So that means the slip in here equal to 1 because stand still. Yeah, that means ns minus n over n. So this equal to 0, so that means equal to 1 in here. And then in this region, ns minus n over ns, but now this equal to ns, so equal to 0, right? So that's how you can see that. So now, when you see many literature, they will also use this kind of the slip to show you the horizontal axis. That's how it look like anyway. So now then, I have labeled two regions, unstable and stable region. Anybody can tell me why it look like this? Why this one region called stable, one region called unstable? That's the important point I has been talking about for the whole lecture, right? Why this region called stable? Of course, stable region, that means we tend to move the motor to this region of operation. That's a preferred region. Why is that? Anybody can tell me why? I think you've seen that curve, right? Everybody has seen that motor curve. You have learned that in the past, but tell me why this stable? Why the other side will be unstable? So the differentiate.
That's the reason we get after once it achieves the maximum torque region. After that, it start decreasing.
Yeah.
So that's what stability we get.
You see all the characteristics, all the efficiency characteristics, all the power characteristics, they also have a maximum somewhere, and the other side will be decrease. No matter horizontal axis, like power supply, we got output voltage or the output power, then we have top efficiency, and the other side will drop. Happen to all the systems. Any system should look like this. But now my question is, why the right-hand side region is stable? Why that is stable? Why this unstable?
Even if the speed is increasing, it is decreasing. Like
Because like
the torque is decreasing even if you increasing the speed. That's why it's stable.
Okay, maybe sit down. Any other comment?
Why is the unstable?
Let's say.
Because the motor is already in motion, because we need to like put so much torque onto the motor and so much force on the motor to bring it to a like the maximum or the breakout torque till then, but after a certain point when the motor is already rolling, right? We don't need that much torque to increase the speed.
Let's
So-
try to discuss in another way. For instance, you have a battery. When you put more load, more resistor there, then voltage will drop.
Mhm.
And then when we remove the resistor, the voltage will return to original. It won't differ by that much. Like the PG&E power distribution here, when you plug in, it's 120 volt. When you plug in a lot of the hair dryer, you draw the load, the voltage may drop slightly. And then when you remove the hair dryer, the voltage will go back. So there's a natural feedback control in the system called the loading effect. Similar to here in this operation. You see, when you operate in here at certain speed, when you draw higher torque, putting more loading, the torque will go to here, and the speed will become lower. The speed will reduce. So that means drawing more low torque, the speed will decrease. When you remove the torque back to here, the speed will go back up. So the natural phenomenon for internal feedback for loading effect, that's a more natural way to understand loading effect. That's the same for all the motor, all the power source. Every system should look like this. That's a normal operation. That's so-called the stable operation. That's what I meant for internal feedback, internal stable situation. Okay? So that's why we like the motor to work on this region. So can you correlate that? The torque speed to a normal power distribution or battery source, right? We know that. That's naturally, we know that all the system behave. That is much easier to control because when you try to reduce the low torque, increase the low torque, you know how the speed behave. That's a normal. But however, in this region, it's something different. If we got certain speed in here, then if we try to remove the torque, low torque, you lose the loading, the speed will decrease. That's different from what we think. And then you try to restore it, you try to decrease more torque, the speed will continue to decrease until it becomes zero, stall, the motor stop. You can't do anything. So that the region of unstable, inconceivable, you can't operate the motor in such a way because it's abnormal, normal. So that's why we call it the point of low return. You see that just now? I mentioned to you point of low return. We don't operate in that region. We tend to operate on the normal operation state region. So low return is something we need to avoid. So that means that's the curve for motor operation. That is to say, when you input certain voltage, say 120, maybe 240, whatever voltage you input to the motor, then you tend to start the motor in here, and then you will increase the motor speed to here, and then you tend to operate the motor in this region. So just now you say 25 to 50 will be more in this region, right? That's 50, right? 50. So that's a more look like in this region. That's a more reasonable. So you won't go, once you go over here, you are dangerous. The motor will stop. So that's why motor control, if you tend to increase the motor torque, when you go at that region, after that region, the motor will stall. You move to here. So that means it's stalled. Right? So that region operation, we need to be really careful to operate on industrial motor. And then the motor, so these two regions are, we call the safety region, right? Stable region. This is also stable. For electric vehicle, positive region then become power regeneration. The motor power will return to the power source, return to the battery. So both of that will be define the most quadrant 1 and quadrant 2 operation. So how it look like. And this region is called the braking region. When the vehicle is braking, so that's called the plugging. I think we also mentioned the plugging. When you tend to reverse the voltage to stop the motor, then go to this region too. But basically, we more focus on this region. That's a normal, stable region. So beyond the zero speed here, the zero synchronous here, the motor will start to reverse into higher. That means the motor will become higher speed, the synchronous. You see, tell me why this region called power regeneration? Before we have 1 minute to go away. Why this region? Can you tell me why this region I call it power regeneration? Can you?
With less power, speed is increasing.
You see, in the power regeneration, we using the frequency to understand more about which power flow to which one. You see, in this motor and the DC motor different. DC motor, you see, we use voltage, right? But now we use frequency. At that particular frequency, full frequency input and the motor are equal frequency, become low induction. And then at here, the motor frequency is higher than the synchronous frequency. Like 50 Hz, now the motor becomes 51 Hz.
So the rotor makes the induction.
The motor is running faster than the input frequency. Then the power will flow from the rotor back into the stator. So linear frequency. So if you want to control motor, become generator, what we need to do is to run the motor faster, like the water power generator, wind power, run it faster than input. Then we go to this region, we will therefore flow the power back. So that's how we operate the power regeneration. So that's why in this region, the speed is less than 1 because the motor speed is higher than the synchronous. So in here, so this is larger, that's smaller. So that's why become negative, right? So that's how it operates. So remember, industrial motor, we use frequency to control it become power regeneration. Okay, that's the concept. The final. Okay, we continue next week. So I'd like you to, this curve is so common, everybody know, but I'd like to think more carefully how it operates, what it is, and then you can develop more new theory of operation. If you, in the future, you like to do electric vehicle research professor, this is something starting up you need to know about. Everybody need to know. For research student, your understanding would be much more than the undergraduate because how you understand the operation, power regeneration, mode operation control, you need a deep understanding because you're going to teach the student. So you understand not only the equation is this zero, negative, positive, not only this, you need to understand the physical meaning, how we do the power flow, why we have the frequency there, why we have frequency there. So I need to 100%, 1000% of understanding. All right. So we stop here and then we.
Last one.
Okay.
Like regeneration.
Regeneration, you see, the slip here will be negative. Here will be 0. Slip equal 1, here slip will be negative, less than 0.
Yes.
At that time, the motor speed, the rotation speed will be higher than the synchronous speed, higher than the input
You mean
AC.
synchronous means stator speed.
The stator speed, the stator frequency. The input frequency means the stator frequency, the synchronous frequency.
Yeah.
We need the rotor have high speed to the synchronous frequency so that we can feed back energy to the stator. Which one have high frequency, where the power come from? Okay. That's the rule of thumb for the induction motor. They use frequency, the induction to control power flow. Of course, that will be related to voltage. On this curve, you can see that we are using frequency to control which one is motoring, which one is regenerating. That is the rule of thumb for the power generation or the generator. The generator and this region, because the rotation speed for the wind power is higher than the input 60 Hz, then we can have power generation. So that's why we can control the rotor speed for the wind turbine. So if the wind speed is too low, we have low generation. we need a certain wind speed, we can start the generator for the low motor, for the wind turbine. So that's so-called the plug-in speed for the wind power generation anyway. But we don't have too much time. When we, in the future, we learn about the wind power, then we can discuss more about that. Okay, good. See you again next, no, not next week, Thursday. Yeah.